Hi everyone, this is Rasik Rashid Malik and today it is week 12 problem solving and discussion session for the course Fundamentals of Semiconductor Devices. Let's start this session. I'll start sharing my screen. I hope my screen is visible. Today we'll be talking about the optical devices, solar cells, optical absorption, solar cells, uh, photodetectors, LEDs and so on. So let's start today's session. The first question is about the optical absorption, where we have to calculate the thickness of a semiconductor that will absorb 90% of the incident photon energy. Before solving this question, let's give a brief overview of the optical absorption, because this comes under the optical devices. So far we have been discussing about the physics of transistors that are used to amplify the electrical signals. We talked about the MOSFETs, we talked about the diodes, heterojunctions, and so on. And then there are the special type of semiconductor devices that convert optical energy into electrical energy, or that convert electrical energy into optical energy. So these type of devices called the optical devices that we will be talking about. So, and then general, these devices are used in broadband communications and data transmission or optical fibers. So the general classification of these devices uh, is called optoelectronics. The first topic that we will be talking about is the optical absorption. So before talking about the optical absorption, we know from the wave particle duality that indicated light waves could be treated as particles, which are referred to as photons, and the energy is given as energy of the photon is given as E equal to h nu, right? Where h is the Planck's constant and nu is the frequency. We can also relate it to the wavelength, like we in terms of in place of this the energy we can relate in terms of the wavelength, because wavelength is the velocity of light into the frequency, and hc, and we can write as if I multiply it by Planck's constant both in the numerator and denominator, I can write it as hc by h nu, or that is hc by energy. And if I substitute the value of the speed of light and E and the Planck's constant, so and I keeping energy not in the joules but in the electron volts, so this comes out to be 1.24 E is in electron volts, and this limit will be corresponding to micrometers. Okay, so now talking about the optical absorption, because there are several possible photon semiconductor interactions. Because if I talk about the photon semiconductor interactions, photon can interact with semiconductor lattice, whereby photon can be converted into heat. Okay, they can interact with the impurity atoms, either donors or acceptors, or they can interact with defects within the semiconductor. However, the basic photon interaction. So I was talking about the photon semiconductor interaction mechanisms. Photon semiconductor
interactions. So in a semiconductor photon, it can interact with lattice.
interaction with the semiconductor lattice,
And wherein the photon energy into heat may be converted. Or then photons can also interact with the impurity atoms. Or defects.
within the semiconductor, right? However, the photon interaction process that is of great interest is when photon collides with the valence electron, and then the energy is given to the inverted electron into the conduction band. Such a process may lead, for example, that I am saying that photon colliding with a valence electron.
Okay, and then when it interacts with the valence electron, it elevates it. The electron goes from valence band to conduction band. So if that happens, then the outcome will be electron hole pair or the excess carrier generation or the electron hole pair generation.
So the behavior of the excess carriers has already been studied in the previous lectures. So the optical absorption is, we'll be talking about this type of electron hole pair generation, where a semiconductor absorbs the optical energy and then how it can result into the electron hole pair generation. Okay, so when a semiconductor, let me create a new slide here. When a semiconductor interacts with light, so we have now a semiconductor and it is illuminated with light. So it may be photons,
They may either be absorbed or they may propagate. Or the photons, when we shine light on a semiconductor, they may just propagate through the semiconductor without doing anything, right? So when semiconductor is emitted, is illuminated with light.
so when the how what it will depend on, so it will ultimately depend on the photon energy and the band gap.
So this type of behavior, it will depend on photon energy and band gap of semiconductor.
Okay, so the case one will be when the photon energy will be less than the band gap. I will write it as this is as a photon energy when this photon energy will be less than the band gap of the semiconductor. Okay, so if this is the case, the photons are not absorbed. So I will write it as this is case 1, this is case 2. Okay, so if this is the case when the photon energy is less than the band gap, the photons are not absorbed.
So in this case, the photons are not absorbed.
So the semiconductor is transparent for such a case. Okay.
Semiconductor as transparent. So if the energy of the photon is less than the band gap, so the semiconductor is act as transparent.
But there will be other cases uh, where the photon energy will be greater than the band gap or equal to the band gap or
The greater than the energy band gap. So in this case, the photons can interact with the valence electron and then raise the valence electron to the conduction band.
and then so in this case I will write it as photons can interact
with valence electron, and then when that happens, it valence electron goes into the conduction electron,
and then there will be the electron is in the conduction band and the hole is in the valence band. So the probability of interaction is high.
and there will be another case when h nu is greater than Ag. So in this case, there are higher chances that there will be interaction with the valence electron.
Okay, so the result of this that we have electron hole pair ratio.
Right? So the processes that I told about, I will just write here. So say we have conduction band and we have valence band,
And then the case one which I
said that when the photon energy h nu is less than the band gap. So if it is less than the band gap, so the photon, the valence electron will not be reached. So say this is my h nu photon and it is less than,
so it cannot make the interaction of the valence electron with the conduction electron. It is not possible. So for this case, it is the transparent case. And then there will be another case, say when the h nu is equal to the band gap. So in that case, the electrons
may be raised to the higher band gap, to the from valence band, and when electron goes from valence band to the conduction band, so the electron hole pairs are generated.
And then there will be the third case, say h nu greater than Eg. So in that case, the valence electron may go into the conduction band. Okay, and in that case, there will be then excess energy. This excess energy can be given to the electron or the hole as the additional kinetic energy. so which will be then dissipated as heat. Okay, so this will be the case for this type of an electron, and for the similarly for the hole, the additional kinetic energy may be dissipated as heat. So the figure this summarizes the optically generated electron hole pair from the photon energy. So let's create a new slide here. Say we have the intensity of the photon flux as IV. IV is usually in the units of energy per centimeter square second. So this represents the intensity of the incident photon flux. Right? So, and say this was a semiconductor, and we are applying we have the incident photon flux say at position x. This is position x and this is x plus delta x. So the incident flux say this is IV at x, and this is the outward flux. Okay, so the energy absorbed in this distance dx so that will be directly proportional to the incident flux for the distance dx, and there will be then this constant
which is called as the absorption coefficient, alpha.
and alpha is in the units of per centimeter. Okay, so from this figure I can write it as IV at x plus dx. Using Taylor's expansion, I can write it as IV at x plus differential of IV with respect to x into dx. So that I can write IV at x minus alpha IV at x dx. So negative here represents the absorption. So that means we have div of x by dx equal to minus alpha x, or by solving this we'll get IV at x
to be equal to IV 0 exponent of minus alpha x. Okay, so this represents the intensity of the photon flux.
It decreases exponentially with the distance through the semiconductor material. Okay, so if I draw this diagram of alpha v IV of x as a function of the distance to the semiconductor medium.
So when the photons are photon flux, its intensity it will decrease. Say this was the incident photon flux, and
it will decrease exponentially, and it depends on the semiconductor material. And different semiconductor materials will have different alpha particular for different wavelengths. So say this is for a semiconductor material for small alpha, say, and when the alpha is larger, so it will be more steep. So this is the photon intensity versus distance for the two absorption coefficient, right? But what about now we'll talk about this absorption coefficient because it depends on the semiconductor material and also on the photon energy. And we have here the diagram where it shows that the absorption coefficient alpha that we are talking about. So it depends on for different materials as a function of wavelength. Okay, this absorption coefficient increases very rapidly when h nu is greater than the band gap. So as you can see here in this diagram, so let's take a special case of say silicon. So silicon, you see when the band gap is around 1, when the band gap increases, you see the absorption coefficient becomes very steep. So when the photon energy is very high or very higher than the band gap, so the absorption coefficient, value of absorption coefficient increases. Or you can say similarly for the wavelength, when the wavelength corresponding to greater than corresponding to the band gap, so the absorption coefficient becomes very steep. Like when the wavelength decreases, means the energy is greater than the band gap, so the absorption coefficient becomes very steep. And for h nu greater than Eg, less than Eg, when h nu is less than Eg, so we have a very small value of absorption coefficient, so that means the photons are not absorbed, so the semiconductor is transparent. And for h nu greater than Eg, when the photon energy is greater than Eg, so alpha increases very steeply as a function of photon energy. It increases rapidly with Eg. So this is the learning from this diagram. And then the diagram on the right, it shows we have the different materials, the relationship between band gap. For example, the zinc arsenide, corresponding to zinc arsenide, we have the band gap this and the wavelength this. So we may note that for the silicon over here, and for gallium arsenide, they will absorb all the visible and all the visible spectrum, because corresponding to visible spectrum we have, this is the normal optical range, our optical eye response, to this. And then when the band gap is higher, this is the case for red, for the visible spectrum, red to violet, so it will, the silicon as well as the gallium arsenide, they will absorb all the energies of the visible spectrum. Whereas if we talk about the gallium phosphide here, gallium, it will be transparent to the red spectrum, because red spectrum is on the left side, so the energy corresponding to this red spectrum is less than the band gap of the gallium phosphide. So this is very important. And now we'll start solving our questions for today. So the first question is about calculating the thickness of the semiconductor that will absorb 90% of the incident energy.
We have a semiconductor, and where the wavelength is given, and in the second case we have a different wavelength. For the different wavelengths we have different absorption coefficients. So that is what the question is about, and we already know. So the first thing will be, since this is for silicon, and for the different wavelengths we are given two wavelengths, one micrometer and
and another is about 0.5 micrometer. So this is 0.56 and this is somewhat around 0.5. So the absorption coefficient in case of silicon for the two will be different. For the lower wavelength it will be absorption coefficient will be higher, and for the higher wavelength the absorption coefficient will be lower. So I will write the value of the absorption coefficients for the two values. So when lambda is for silicon, this is when lambda is 1 micrometer, we have alpha equal to 10 to the power 2 per centimeter. Okay, in the second case, when lambda is 0.5 micrometer, we have alpha will be higher, so that is 10 to the power 4 per centimeter.
This we can get it from this diagram. So this is the case for 1 micrometer, and this is the case for
0.5, and this is 1. Okay, so now we know the value of the absorption coefficient, and we have to calculate the distance, say where the 90% of the incident photon is absorbed. Say let x equal to d is the distance where up to which the 90% of the incident flux is absorbed. Okay, then we can write or what does that mean? Mean is 10% will be of photons will be emergent. Will be emergent at x equal to d. So we can write intensity or the photon flux at distance d by incident photon flux IV at 0. So that will be 0.1. So this will be the 10%. So that means that will be equal to E alpha d. Right? So this is the case because we have already derived it in the previous section here. IV at any position x is the IV at 0 e power minus alpha x, and we now already know that IV at d is the 10% of IV at 0. So that means IV at d will be IV 0 e power minus alpha d. So now d, we can calculate d. D will be simply, alright, we'll go to the next slide. So from this relation d, I can write as, we have 0.1 to be equal to e to the power minus alpha d. So taking logarithm on the both sides and then taking inversion, d will be simply 1 by alpha ln of 1 by 0.1. So that is equal to 1 by 10 to the power 2 for case 1, when lambda is equal to 1 micrometer. So that will be 1 by 10 to the power 2 ln of 10. So that is, we have calculated, it is coming out to be equal to 0.023. Okay, and now consider the case second. where lambda is 0.5 micrometer, and corresponding to lambda equal to 0.5 micrometer, we have alpha as 10 to the power 4. So d will be 1 by 10 to the power 4 ln of 1 by 0.1. So that is coming out to be equal to, it should be same value except divided by 10 to the power 2 again. So that is 2.3 10 to the power minus 4 centimeter, or 2.3 micrometer, and here it is in centimeter. So what did we learn from here? That as the incident photon energy increases, or when the wavelength decreases, so learning is that as the incident photon energy increases, the absorption coefficient what happens to the absorption coefficient? It increases rapidly, and if it increases rapidly, so the photon energy can be totally absorbed in a very narrow region at the surface of the semiconductor. So the photon energy can be totally absorbed. In a very narrow region. Surface of semiconductor. So here we found how the absorption coefficient depends on the band gap, depends on the wavelength, and the incident wavelength or incident photon energy. Okay, so now let's move to the next question. Here again we have a 5 micrometer thick silicon, and we have to determine the percentage of photon energy that will pass through this slab, and we have again lambda as 0.8 and lambda as 0.6. Okay, so the first thing will be to calculate the absorption coefficient corresponding to two wavelengths as we did in the previous question. Okay, so from that diagram, when alpha is 0.8 micrometer, so it will be somewhat close to the 10 to the power 2, so that is 10 to the power 3 actually. If we look into the diagram, the case where say it is 10 to the power 3 here, for 0.8, and for 0.6 it is somewhat in between 10 to the power 3 and 10 to the power 4. So the actual values are when lambda is 0.8 micrometer, we have alpha as 10 to the power 3, and for the other case when it is 0.6, alpha is around halfway, somewhat 4.5, 10 to the power 3. per centimeter. So this is the case when lambda is 0.6. Okay, so now we have again the distance is given,
and we have to determine the percentage of photon energy that it passed. So the distance is x equal to t, that is given to be equal to 5 micrometer. We'll write it in the centimeter units, so that will be 5 into 10 to the power minus 4 centimeter. Now for the case 1, this is case 2. For the case 1, when lambda is 0.8, we can write IV at distance d, so that is the complete thickness of this slab, and IV at 0, so that will be e power minus 5. So that we can calculate. Alpha we already know, it 10 to the power 3 for case 1, and distance is 5 into 10 power minus 4. So the value is coming out to be equal to is 0.607. So that means for the case 1, 60.7% of photons will pass through the slab. Because this is IV at D, means the photon flux emerging at distance D. So 67% of photons are emerging, or will pass. I will write as will pass to the slab. But what if now the wavelength is changed, say to 0.6? Let us go to the next part of this question. Case 2, when lambda is equal to 0.6 micrometer. So for this case, minus e power minus alpha d, and that is exponential of, we already calculated alpha for this as 4.5 10 to the power 3, and that d is 5 into 10 power minus 4. So if we calculate it, it is coming out to be equal to 0.105. So that is equivalent to 10.5%. So we see that when lambda was 0.8 and the case 2 was 0.6 micrometer, so here 60.7% of photons were emerging, and here just 10% of photons are emerging, means the rest of the photons are absorbed. So when the wavelength is less, more absorption. Less wavelength means higher higher E equal to h nu. If it is greater than the band gap, so means more absorption. So I hope this is now clear about the optical absorption.
we will be talking about the next topic, the generation of electron hole pairs. So before solving this question, let me again give a brief introduction about the electron hole pair generation. So we have seen now if the photon energy is then the band gap, it can be absorbed, creating electron hole pairs, right? So if h nu is greater than Eg, so what will happen? So photon
Energy will be absorbed
and then the result will be electron hole pair generation, right? If say we have IV at X is the photon flux, and that is in the units of energy per centimeter squares per time, and alpha IVX, so that is actually the energy absorbed per unit volume, is the rate at which
energy is absorbed per unit volume of semiconductor.
so if we assume that, so this is the rate at which the energy is absorbed per unit volume. If we assume that one absorbed photon with the energy h nu creates one electron hole pair, then the generation rate will be simply, so this is G dash, say generation rate of electron hole pairs, and it will be in the units of number of electrons suppose generated per centimeter cube per second. So that will be simply then equal to alpha IVX, so that indicates the rate at which the energy is absorbed per unit volume. So if we divide it by photon energy, so that will give us the number of electron holes that are generated and when the photons are absorbed. So IVX by h nu is called the photon flux. So that is alpha into IVX and h nu. This IV by h nu is called photon flux. If on average one photon produces less than one electron, so this is the case where we have assumed that corresponding to one photon we have one electron hole pair. But if one absorbed photon produces, say, if one photon produces
Less than one electron hole pair.
then we have to multiply it by the efficiency factor. Say this is my equation.
We have to multiply it by the efficiency factor. Okay. So now let's come to the question.
which where we have to calculate this generation rate of electrons and holes at a given instant intensity of photons. And we know that for this generation now, it depends on the absorption coefficient and the photon flux. So the incident intensity of the photons by photon energy. So that is the photon flux into the absorption coefficient, and it will be in the units of number of photons per centimeter cube per second. So for this, we first have to calculate the energy of the photon and the absorption coefficient. And since this is gallium arsenide, and we have to look into the figure again, when lambda is 0.75 micrometer, what is the value of absorption coefficient? What is the value of? So that we can compute from this figure. This is the case of gallium arsenide, and we have alpha lambda as 0.75. So 0.7, if it is this, 0.75 will be like this.
And so for this case, for the gallium arsenide, so it will be somewhat close to 10 to the power 4, and if I write the actual value, it is 0.9 into 10 to the power 4
per centimeter. So this is the first thing that will be required, and we have to calculate h nu, because lambda is given, and we have to calculate the energy of the photon. So this is the absorption coefficient. Now we will calculate the photon energy. So the photon energy is simply h nu, and we establish it we first derive the expression for the photon energy and the wavelength relation, that was 1.24, and if we divide the wavelength, it should be in the micrometers, and the energy will be in the electron volts. So the value is coming out to be 1.65 electron. So this is the photon energy, and we know that it is greater than the gallium arsenide band gap, which is 1.424. So the most of the photons will be absorbed, and corresponding that absorption of photon, this 0.75, you have to note that this is the typical intensity of the sunlight here. So, and now the generation rate we have to calculate. So the generation rate G dash will be simply alpha, the value of alpha is now 0.9 into 10 to the power 4, and then we have IV at X is 0.05. It is in the watt per centimeter square, so that's good. And then we have to divide it by h nu, so that is 1.65. But here the case is the photon, the energy IV is in the watt unit, so we have to calculate this 1.65 into joules, so we have to multiply it by 1.6 into 10 power minus 19, and result will be that we will have the value in the units of per centimeter cube per second. Let's calculate this value. 0.9 into 0.05 divided by 1.65 divided by 1.6. So the value is coming out to be 1.7 into 10 to the power 21. So this is the generation rate, and if the incident photon intensity is already in the steady state, then we can also calculate this is the generation. We can also calculate the excess carriers, the minority excess carriers. Okay, say if we assume that the excess carrier lifetime is tau is 10 to the power minus 7 seconds, which is the typical value of the recombination time. So the delta n, the excess carriers, will be then simply the generation rate and the tau. So that is 1.7 10 to the power 21 into 10 to the power minus 7. So it is close to 1.7 10 to the power 9 10 to the power 14 per centimeter cube. So this is the excess carriers. So this example gives us an indication of the magnitude of electron hole pair generation rate, right? So, and the magnitude of excess carrier concentration that we can have when the photons are absorbed. And as the photon intensity will decrease with distance, the generation rate will also decrease, because we have seen how the photon absorption will decrease, or the intensity of the photons will decrease as we go deep into the semiconductor. So this generation rate and the excess carrier generation rate, excess carriers will also decrease. Okay, so now let's solve a few more questions on this. So the first question is about, we have a photon flux with the intensity of 0.1 watt per centimeter square, and the wavelength is given, and the semiconductor is silicon. And for lambda equal to 1 micrometer, we already know it is 10 to the power 2 at the absorption coefficient, and neglecting any reflection from the surface, we have to determine the generation rate of electrons and holes at a data 5 micrometer and 20 micrometer from the surface. So the starting point will be at lambda equal to 1 micrometer. We have partial alpha
to be equal to the power 2. And at this wavelength, we have to calculate the photon energy equal to h nu. So that is 1.24 divided by wavelength in micrometers. So that is 1.24 divided by 1. That is 1.24 electron. Okay. Now coming to the first part of the question, where we have to calculate the generation rate at x equal to xt. So for that, we first need to have an idea of, because the generation rate is alpha, we know IV at x, and then h nu. So h nu we have, alpha we have to calculate IV at distance x equal to, say, 5 micrometer for the first case. Okay, so that is simply IV incident, that the value we have, and exponential of minus alpha d, and d is, so I can write it as 0.1 exponential of minus 10 to the power 2, and the value of alpha is 5 micrometer, so 5 into 10 to the power minus 4 centimeter. So let's calculate this value.
And it is coming out to be equal to 0.0951
watt per centimeter square. And so for this case, the generation rate will be simply alpha,
that is 10 to the power 2, and IV at x equal to 5 micrometer, that is 0.0951. Since this is in watt, the SI units, so we have to multiply
the photon energy by the electronic charge. So the generation rate will be is coming out to be equal to 4.79 into 10 to the power 19 per centimeter cube per second. Now let's go to the second part of this question. Where we have to calculate IV at x equal to now 20 micrometer. So that will be equal to IV at 0 exponential of minus alpha into x. So that is simply 0.1 exponential of minus 10 to the power 2 into 20 micrometer. So 20 into 10 to the power minus 4 centimeter. So that is equal to 4. That is coming out to be equal to 0.0819. So you see the intensity will decrease as the x will increase. Watt per centimeter square. Now the generation rate will be equal to alpha IV at this x equal to 20 micrometer and divided by h. So that is simply 10 to the power 2, 0.0819, and the energy in joule units. So the generation rate will be now less because x is 20 micrometer, x is larger, intensity is less, so the generation rate will be less. And the generation rate is coming out to be equal to 4.13 10 to the power 19 per centimeter cube per second. So earlier it was 4.79, now it is 4.13. So this is a typical value of the generation rate here. Now let's move to next question. So it says again we have a photon flux at IV at 0 is 0.1. We have is incident on surface of silicon, and the wavelength is given alpha lambda is given by 1 micrometer, and we have to neglect any reflection from the surface. We have to determine the photon flux at the depth of 5 micrometer, 20 micrometer from the surface. Okay, and then we have to repeat this question at 0.6. Okay, so if we start calculating, we know that the IV at any position is IV at any x is equal to IV at 0, that is given exponential of minus alpha x. And if we go to the first part of the question, and where lambda is equal to 1 micrometer, we know the absorption coefficient for silicon corresponding to 1 micrometer is 10 to the power 2 per centimeter. And if we now go to the first part of the question, that is x equal to 5 micrometer, IV will be simply 0.1 is the incident flux exponential of minus 10 to the power 2 into 5 into 10 to the power minus 4.
So that is simply equal to 0.0951 watt per centimeter square. And as the distance will increase,
the intensity will decrease. IV, which is now 0.1 exponential r minus 10 to the power 2, 20 into 10 to the power minus 4.
so let me calculate it. It is coming out to be equal to 0.0819. So this solves the part A of the question, and we got the values, the first two values in the answer. And the next part is similarly, just for that wavelength we have to calculate the absorption coefficient. Let me put a new slide. So the part B of the question says that we have now lambda equal to 0.6, and for silicon in the previous question we know for this value the alpha is 4 into 10 power 3 per centimeter. So the first part, for part B, x equal to 5 micrometer, we will have intensity to be equal to 0.1
Exponential of minus 4 into 10 to the power 3 into 5 into 10 to the power minus 4.
Let me calculate it. It is coming out to be equal to 0.0135 watt per centimeter square.
And the part B of the question, x equal to 20 micrometer.
We will have IV to be equal to 0.1 exponential of minus 4 into 10 to the power 3 into 20 into 10 to the power minus 4.
That is equal to
3.35 into 10 to the power minus 5 watt per centimeter square. Okay, so this solves this question about the optical absorption. Let me move to next question. So the next question is about now the solar cells. Before starting solving this question, again we will briefly discuss about the solar cell. Let me insert a new slide here. So the solar cells. Solar cell is a type of PN junction. We have a PN junction device with we do not apply the voltage directly across the junction. Okay, so it's a kind of PN junction device. And what happens is it converts the photon power into the electrical power. It converts photon power into electrical power, and then this way it delivers power to the load. this is a simple principle. These devices then have been used, can be used as power supplies, for satellites, space vehicles, etc. Are some calculators as well. So we'll first discuss about the simple PN junction solar cell, where we have a uniform generation of carriers, and then if time permits, we'll discuss about are the heterojunction or the amorphous silicon solar cells, or we can directly move to the photodetectors. The next part of this optical devices. Okay, so let's now first talk about the PN junction solar cell. So we have a PN junction solar cell. If I draw it here, simply we have a PN junction, and during the reverse bias we have some depletion region. Say this is the junction, and then we at zero bias we have some space charge existing. Okay, and then in the space charge we will have the electric field. The direction of electric field will be like this. So we will have electric field corresponding to this space charge region, and then the photons are incident on this depletion region h nu. So what happens is that electron hole pairs are generated. So let me write it over here. We have a PN junction, and then we have it is depletion region, and then this h nu, it generates electron hole pairs, right? So but then we have this electric field, and so these excess electron and hole pairs are swept if we have a load connected to this PN junction. Say this is my resistor R. So corresponding to this load we will have a photon current. Say we will have current this direction, in the reverse direction actually. So as the current will flow into the resistor, so we will have a voltage drop across it, and now this voltage will try to forward bias the junction, and with the forward bias the depletion width will try to shrink. Okay, and the net current, so with that we will have the forward component of the current, say IM. Okay, so the net current will be then simply IL minus IF, and this current will be negative, so actually this is the third current, and the voltage is positive and the current is negative, will be simply IL minus IS into exponential of EV by kV. This is the simple expression for the forward current IM. Okay, but the current of interest will be IL minus IF here in this case. So this if IF, when IF flows, so the electric field will decrease, but the magnitude of the electric field has decreased, but it does not go to zero, or it does not change direction. So the photo current will always be this photo current will always be in the reverse direction. Okay, so photo current will be in reverse bias direction. Okay, so now we have, let's consider this equation, and then we will have the two important cases of limiting cases of interest. One is called let me insert a new slide here. So we have now the expression for the current, that is IL minus IF, that is equal to IS IL minus IS exponential of minus EV by KT minus 1. So this is the net expression for the current, and the two limiting cases will be the short circuit condition. Say case 1, when R is 0, that is called as short circuit condition. Okay, so in this condition, when R is 0, so if R is 0 means V is 0. So if V is 0, R is 0, V is 0, so the net current will be I will be simply IL, or short circuit current, that will be simply IL. Okay, and the second limiting case will be if R is infinity, means when we have the open circuit condition. So for this open circuit condition, the photo current will be just balanced by the forward current, right? So for that case, we will have net I equal to 0, because no net current will be flowing. So internally, IL will be balanced by IS. So IL minus IS into exponential of EV by KT minus 1, that will be equal to 0. And we will have corresponding voltage as open circuit voltage. So we can find this open circuit voltage by just reversing, taking IL to right hand side, dividing by IS, and then taking logarithms. So this will be VT. VT is just KT by E into ln of 1 plus IL by IS. So if we plot this I versus V, this from this equation, we may note that the short circuit current, we can actually write it here. Say we have this voltage over here, and then we have the current over here. So we have the two limiting cases now. When current is 0, the voltage is the highest voltage will be open circuit voltage, and when the voltage is 0, for the short circuit condition, we will have a negative called the short circuit current. Okay, so in between, the expression will be like this. So the graph will look like this. So this is the VI characteristic for a solar cell. And this is I. Now the next part of the question will be on the power. So before moving to the power calculation, is we'll move back. We'll first to calculate about this. We'll first to solve this question, which is about calculating the open circuit voltage of the solar cell, and we are given the parameters where we can actually calculate the IF, and sorry, IL, we can calculate the solar cell current. So, and we are given the various values N, A, D, and tau and 0, which may be used to calculate the saturation current IS, and then from that we can actually calculate I are the other values, because we have to calculate the open circuit voltage. So if we have to calculate open circuit voltage, we will need IL, we will need IS and VT. VT is simply IL and IS we will need. So to calculate IS, we have to calculate, that is the reverse saturation current. We can calculate from these values. We have already derived the relations in the previous lectures about IS. And then IL is already given here. So from that we can calculate the open circuit voltage. Okay, let me just write the expression for the open circuit voltage, which is given by Vt ln of 1 plus IL by IS. So you might be knowing that the reverse saturation current density Js, which is nothing but Is by area of the junction, so which is E dn mp0 divided by ln and E dp pn0 divided by L, that we have already calculated in our previous sessions, the expression, or we can write it equal to ENI square, because NP0 can be computed from the doping, Ni square divided by doping. So Ni square I have taken out, so that is now simply dn by ln into doping Similarly, dP by Lp into Md. And Ln, we can easily calculate Ln and Lp. Under root of diffusion coefficient into recombination time. So for the case 1 it is 25 and tau is 5 into 10 power minus 7. So that is coming out to be equal to 35.4 micrometer. Okay, and similarly we can calculate Lp. Let me go to the new slide. So Lp will be simply, as we calculate the Ln as dp tau p0, and we have already values for dp and tau p0 given in the question, 10 and 10 power minus 7. So that is equal to 10 micrometer. So the reverse saturation current density can be then found to be equal to E 1.6 into 10 power minus 19, and then Ni square, that is 1.5 into 10 power minus 10, and then we have Dn, that is 25 divided by Ln, that is 35.4 into the doping 5 into 10 to the power 18 Na, and then we have 10, that is dp divided by Lp, that is 10 into 10 power minus 4. Here again we have to write 35 into 10 power minus 4 into the doping Nd, that is 10 to the power 16. So let me calculate this value. So the value is coming out to be equal to, for the Js, as 3.6 into 10 to the power minus 11 ampere per centimeter square. So then from this expression VOC, we can calculate the open circuit voltage, that is VOC equal to Vt ln of 1 plus IL by IS, or we can write in terms of current densities. So that is simply 0.0259 ln 1 plus JL. JL in the question is given 15 into 10 power minus 3 divided by the reverse saturation current, that is 3.6, 10 power minus 11. So let me calculate this value. The value is coming out to be equal to 0.514 volts. So if you note that this is the VOC is 0.514, and for these the doping levels that are given in the question, if we calculate the VBI, the barrier potential, that is Vt ln of Na and divided by Ni square. So for this very question it is equal to 0.8556 volt. So the VOC is always less than the built-in potential barrier, that you have to note. Okay, now let's move to next question. Here we have a gallium arsenide PN junction solar cell with the parameters given like in the previous question, and we have JL again given. We have to calculate the open circuit voltage, and then we have to determine the ratio of the open circuit voltage to the built-in potential barrier like we did in the previous question. Okay, let me solve this. So as in the previous question, we can calculate post to JS. So before JS, we can calculate Ln, that is simply dm tau n0, that is equal to 190 10 to the power minus 7. So the value is equal to 4.36 into 10 to the power minus 3 centimeter, and LP similarly has under root of dp tau p0, that is equal to 10 into 10 power minus 8, so that is equal to 3.16 into 10 power minus 4 centimeter. So now we have Ln, we have Lp, we can calculate Js as E(ni square), and then Dn Ln Na plus dp Lp Nd. So that is equal to 1.6 into 10 power minus 19, 1. For the gallium arsenide, Ni square is 10 to the power 1.8 into 10 to the power 6 per centimeter cube. Okay, so it's square. Then we have dp as dn as 190 divided by ln. We calculated 4.36 into 10 power minus 3 into 10 to the power of 70, the doping. Then we have 10 divided by 3.16 into 10 power minus 4 into the doping, 2 into 10 to the power 16. So let me calculate this value. So the value is coming out to be 1.046, 1.046 into 10 to the power minus 18 ampere per centimeter square. Okay, so we find now the Js. Now the other component of the current JL is already given. Let me insert then in new slide. We can calculate the open circuit voltage. We have now Js to be equal to 1.046 10 to the power of minus 18, very small value, ampere per centimeter square. And then we had JL already given in the question, 20 milliamps. Per centimeter square. So we can calculate the open circuit voltage, Vt ln of 1 plus So that is 1 plus JL by JS. So that is 0.0259 ln of 1 plus 20 into 10 power minus 3 divided by 1.046 10 power minus 18. Let me write it here. Into ln of 1 plus 20 into 10 power minus 3 divided by 1.046 into 10 power minus 18. So the value is coming out to be equal to so the value is coming out to be equal to 0.971. And the next part of the question is about calculating the barrier potential and finding the ratio of open circuit voltage to the barrier potential. So VBI is simply VT ln of NAND divided by NI square. So that is 0.0259 ln of 10 to the power 17. ND is 2 into 10 power 16 given in the question divided by NI square. For a gallium arsenide 1.8 10 to the power 6 squared. So that is equal to that is equal to 1.24.
So you already note here that VOC is here again the less than the barrier potential. VOC by VBI is equal to 0.971 by 1.24. That is equal to 0.783. So this solves this question.
Before moving to the next part, so I will again discuss about the solar cells. Let me insert a new slide here. So we'll talk about the power delivered to the load. So that is current into voltage, and we know that that is IL into V minus IS exponential of EV by KT minus 1 into V. So we can find the current and voltage which will deliver the maximum power to the load. So for maximum power, delivered to the load, we will have dP by dV to be equal to 0. So if dP by dV equal to 0, that means IL minus IS into exponential of EVM divided by KT minus 1 okay, and minus ISVM. This is just the derivative of the above equation, E by KT exponential of EVM by KT, where VM is just the maximum, the voltage corresponding to this maximum power. So if that will be equal to 0. So if we rearrange this equation, taking IL to the other side, dividing by IS, and taking 1 also on the other side, so we will have 1 plus Vm by Vt into exponential of EVM by KT equal to 1 plus IL by IS. So the value of Vm can be determined here by solving this transcendental equation. Okay, so if we had to find the maximum power rectangle, like when V is equal to Vm, we can find the corresponding current from that V into I graph of the solar cell. Say this is that we have already talked about, the ISC, this is VOC. Say we have some voltage here which corresponds to Vm, and corresponds to that we will have Im. So the maximum power will be corresponding to this rectangle. Okay, so this is called the maximum power rectangle of the solar cell. And if we have to calculate the conversion efficiency, let me move to the next slide. If we have to talk about the conversion efficiency of the solar cell, so conversion efficiency is simply as the ratio of output electrical power and the incident optical power. So that is the maximum input power by P. So into 100 percentage. So this is the maximum possible current and voltage in the solar cell are ISC and VOC, and the ratio. So since we have the maximum possible voltage is VOC, if we have to calculate, the another factor is the fill factor, which is very also important parameter of the solar cell, which is the maximum voltage, the voltage corresponding to maximum power, and the current corresponding to the maximum power, divided by the maximum voltage with the solar cell can have, that is VOC, and multiplying it by ISC. So that is called the fill factor, and it is a measure of the realizable power of the solar cell. Typically this value is between 0.7 to 0.8. Okay. So now let's move to the next question. So this is about the photoconductor. We have a photoconductor. We have to calculate its gain. So this photoconductor is a special case of a photodetector. So let me insert a new slide to give a brief about this photoconductor. So photoconductor, it is used to detect it is a kind of photo detector. One of the simplest cases of photo detector, which is used to detect the presence of photons. They convert actually the optical signal to the electrical signal. And when the electrical signal is generated, we then say that we have detected the photons. So we have the phototransistor, photodiode, and the simplest cases are as a photoconductor. So we know that in a semiconductor we have the conductivity, that thermal equilibrium is simply E without any photon excitation. Say this is the conductivity. But when there will be the photon excitation, there will be excess carriers generated in the semiconductor, so the conductivity will become E mu n. We will have n0 plus delta n, and then we have mu p, p0 plus delta p. So where delta n and delta p are here the excess carriers. Okay. So here we can assume that delta n and delta p are same, equal to delta n, say, or delta p, and say delta n is equal to delta p. So, and in the steady state we will have this delta n delta p that will be equal to the generation rate of these excess carriers and then the time constant tau p. So we can write this conductivity then to be equal to the E mu n n0 plus mu p p0 and plus E delta p mu n plus mu p. So, and we can calculate the change in the conductivity delta sigma as a difference of sigma minus sigma 0. So this is E delta p mu n plus mu. So this is the conductivity or the photoconductivity. And corresponding to this photoconductivity, we will have the photocurrent IL. That will be simply JL into A, or I can write it to be equal to delta sigma into electric field into area, or I can write it to be equal to EGL tau p mu n plus mu p into AE. Okay, since we know that electric field into mobility is the drift velocity, and if E into mu n is drift velocity, so we can write then that Tn as the electron transit time. I will insert a new slide over here. So Tn, which I call as electron transit time, we will have Tn equal to the length of the semiconductor by drift velocity mu n. So I can write then this photocurrent to be equal to EGL tau p by transit time into 1 plus mu p by mu n into an. So this is simply this expression where we have taken out mu n and then written in terms of the transit time. And the photo conductor gain is, say, pH. It is calculated to be equal to the ratio of rate of at which the charge is collected by the contactors. Let me write it as rate at which charge is collected by the contacts to the rate at which the charge is generated. Okay, so we can write then this gain to be equal to IL, and then the rate at which is generated is EGL AL. Okay, so the gain will be then simply, if I substitute the expression for IL, so the generation rate will be cancelled, A and L will go out, so that is simply tau p by transit time into 1 plus mu p by mu n. So this expression is very important here for the photoconductors, which represents the gain or the photoconductor gain. Okay, so now let's move to the question. Question was saying that we have to calculate this photoconductor gain. Okay, so photoconductor gain, I will write the expression again here. Photoconductor gain is tau p by transit time. Transit time can be found from the mobility and the electric field, and if the length is given, into 1 plus mu p by mu n. So we have here the length is given, so from length and tau p is given, and the mobility values that we already know for silicon, for an electron and for a hole. So I can first calculate the tau n. The transit time is the length of the semiconductor divided by drift velocity. So length of the semiconductor divided by mobility into electric field. So that is equal to length is 10 to the power minus 4 and then we have the voltage given. So electric field can be simply written as V by L. So we have then L square means 100 into 10 power minus 4 square divided by 1350 into voltage applied, so that is 10. So if we calculate this value, it is coming out to be equal to 7.41 into 10 to the power minus 9 second. So now we calculate the first part of the question. Now the second part of the question is about calculating the gain. So the gain now simply will be tau p, value is given 10 to the power minus 6, tau n we have calculated, into 1 plus the mobility of hole is 480, mobility of electron is 1350. So let me calculate this value. So it is coming out to be equal to 1.83 10 power 2. So you should not be surprised about this type of gain in a photoconductor. Photoconductors usually have these high values of gain. Okay. So now let's move to next question. Here the question is, we have a photoconductor, the same photoconductor that we solved now. We have to determine the photocurrent. If GL is given, electric field is given, and the mobility of electron and hole is given to be different here now. For the silicon it was different. So we can solve it here. The photocurrent is simply EGL that we derived into tau p, and then mu n plus mu p into area into electron. So that is simply 1.6 into 10 power minus 19. That is very straightforward here. 10 to the power 21 into tau p is 10 to the power minus, we have already calculated in the previous question as a transient time, 10 power minus 6, and then we have the mobility values 1000 plus 400 into 10 to the power minus 7, the area, into electric field is 10. So let me calculate this value. It is coming out to be equal to 2.24 into 10 to the power minus 7 ampere. So that is 0.224 microampere. Okay. So let's stop here, and thanks for joining